Exponential regression. Ask the question, what exponential function fits best? Let's get some data. Looks kind of like that. All right, now what we want to do is transform the data. The trick to exponential regression is to actually treat it like linear regression. What we have to do is linearize the data, which means taking the log of just the y's. When we do power regression, it's going to be y's and x's, but for exponential, it's just the y's. If we graph this, it looks something like this. Doesn't look too different. Notice that these numbers are really quite different because now, right, they're the log of the y's, not the y values. But really, if we had an idealized exponential graph, something like this, which is perfectly exponential, and we took the log of the y's, it actually becomes perfectly linear. So when we have data which is only approximately exponential, then it's only going to be approximately linear. But theoretically, that's the idea. Now what we want to do is find the linear regression of the linearized data, which is going to be over in L1 and L3. Right, that's our linearized data. So I'm just going to use the linreg function, and we get our linear regression. Now this is, of course, through this graph, which is not our answer. What we want is the line of, or curve of best fit through this data. So what we have to do is transform the equation back into exponential form. The way to do that is you take 10 on both sides and you raise that 10 to the two sides of the linear equation. Now 10 raised to the log of y is just going to be y hat. Notice that what I've done here is reversed the law of exponents. If you have these two multiply together, what do you do with these two exponents? Well, you add them. So I just did it in reverse. The next step, of course, is doing the same thing with this exponent. Notice when you raise an exponent to an exponent, they multiply. So again, I'm just going in reverse. Once you get to this point, all you have to do is actually find what is 10 raised to the 0.409, and you end up with your exponential function. And what we want to do is graph that over the original data just to make sure we haven't made any major mistakes. And you can see it's got a slight curvature, probably fits a little bit better than a linear model. Now, just like linear regression, right, if this was a perfectly linear model, could we fit an exponential? Sure. If it was parabolic, again, it's going to find the best exponential function regardless of the shape of the data. Now, what we can do is look for how to do this on the calculator. Here's our data that I've already entered into the calculator. I'll show two ways. One, to do it by hand. Here, let's get the log of L2. Hit enter, and that's how I got all my log values. And then, of course, you can do your linear regression of L1 and L3. And that should give us, right, our linear regression. It also will give us correlation coefficient. We'll talk about these and the coefficient determination a little bit later. We should be a little bit cautious in using those. That's how you would work the exponential regression, doing it the long way. Now, of course, there is a short way, right? The original data is L1 and L2. And if you go to your stat calc and you scroll down, eventually you will see 0 exponential regression. So we can do exponential regression of L1, L2, which is the original data. Again, I could save this in Y1 or Y2, but it should give us pretty much the same equation, which you can see it does.